in this screencast we're going to look at the delays associated with the ripple carry adder. Serious limitation of ripple carry adders is the fact that there is quite a large propagation delay. Now this is caused because we've got multiple full adders all chained together in a big line kind of thing. So the carry out of one adder feeds into the carry in of the next adder in the chain, and this just repeats for as many bits as we have in the adder. So because it takes a finite amount of time for a logic gate to have the correct output once we've applied an input, it takes this kind of nanoseconds really for the output to be correct, and then so there's a delay until the next full adder in the chain gets the correct inputs. So again, there's another delay associated with the logic gates inside that full adder, and it just keeps passing along this chain. So we're going to do some simple analysis of these delays by assuming that each gate has got the same delay, what we're just going to call the gate delay. So we'll look at a ripple carry adder here. So we assume that the inputs, so we've got our A and B inputs and our carry in, these are all applied at time 0. So it's the first full adder in the chain here, so it's going to take some time for this sum to be correct, and we've actually got to wait until this carry out is correct so this can be fed into the next one. So there's actually a short delay until this sum can be calculated in this carry. Again, there's a further delay then until that carry is presented to this third adder. So there's a further delay until we get this sum and this carry, and so on. So as we go along the chain, the delay just gets bigger and bigger and bigger. So it's only once we've got all 4 bits are correct after this delay that we're sure that the output of the ripple adder is correct. So now we consider what's actually going on inside of the full adders. We're going to look at bit 0 first. So this is the first full adder in the chain, so where the carry in is equal to 0. And we're going to assume that this is for the case when A and B are both 0. So these inputs are applied at time 0. So we can see there's one gate here. So the output of this gate is going to be valid at time 1. And then again we've got this next XOR gate here. So it's at time 2. So after 2 gate delays, so 1, 2, that the sum will be valid. Now for the case where A and B are both 0, we know that the output of this logic gate is going to be 0. So this node here will be 0 at time 1. And then the fact that the carry in this case is also 0 means that this node will be 0 at time 1. And so at time 2 we'll get a carry of this particular case 0, 0. This gives us 0. So for the first full adder in the chain, the sum and the carry are both valid after 2 gate delays. So we'll look at the case now when A and B are both 1. So again, the sum, the sum's still got to go through this path, so the sum's still valid after 2 gate delays. And again, in this instance, A and B are both 1, so the output of this node here, this node will be a 1 at time 1. And because carry in again is 0 for this particular bit, this node is 0 at time 1, so the output in this case, so the carry, is going to be 1 at time 2. So again, for this case, when A and B are both 1, the sum is valid after 2 gate delays, and the carry out is valid and equal to 1 again after 2 gate delays. Now we'll look at the case where A is not equal to B. So again, this case here, the sum is still valid after 2 delays. And again, also in this case, we know A and B, if they're not equal to each other, we know that one of them has got to be a 1 and the other's got to be 0. So we could have this case or this case, but whatever happens in both situations, this node will be equal to 0 at time 1, and again, because this is the first bit in the chain, the carry in is 0, so this node is 0 at time 1. So again, the output will be carry of 0 at time 2. So we can see for the first full adder in the chain, the sum is always valid after 2 gate delays, and the carry out is valid after 2 gate delays. Now we'll look at a more general case now of bit n, I've called it. So this is for a later bit in the chain, so bit 1, bit 2, bit 3, and so on. So essentially, for all the bits for all the full adders in the ripple carry adder, the inputs are applied at T0, and so we know we're always going to have this node here at time 1 because of this gate delay. So for the later bits in the chain, the sum actually depends on the carry in. So if the carry in arrives at T in, we know that there's this additional gate delay here, because remember this, so this input is known at time 1. So the limiting factor is at time when we got a valid carry in. So the sum will be valid 1 gate delay after we've received a valid carry in. And then for the case of the carry out, we can see that's following this path, and that's delayed by 2 gates after the arrival of a valid carry in. So we can look at a 4-bit ripple carry adder now. So again, all the inputs on this first carry in are applied at time 0. So we know for the case of bit 0, so the first full adder in the chain, the carry out and the sum are both valid after 2 gate delays. And so that, well, essentially we can see that we're going to have this valid carry in here at time 2. So the sum for the next bit is delayed by 1 gate and the carry by 2. So again, this full adder will get a valid input at time 4, so the sum will have at time 5, the carry time 6, which is then fed into here. So the sum is at 7 and the final carry 8. So we can see in this particular case, it took 8 gate delays to get a valid answer after we've applied the inputs, and that's just for a 4-bit. So we can make a more general case. We'll look at, this is a table what shows the delays for each stage in the full adder. So the the kind of bottleneck really is the time to calculate this final carry out, and then we can generalize that case for an n-bit adder. The worst case delay is essentially twice the number of stages or the number of bits in that full adder. So we can see in our case we had 4 bits, we got a delay of 8. So you can see that this kind of increases by a factor of 2. So for a 32-bit adder, it's actually going to take 64 gate delays to get a correct answer, which is not really acceptable.